All right, everybody, we're going to get started in a minute.
All right, let's get started. Hi everyone, so I'm Gigi.
It looks a little whack on mine.
Oh, okay.
Sorry guys.
Sorry about this.
It's only showing. Do you want to?
Yeah. All right, sorry about that, technical difficulties, but we are all good. All right, so hi everyone, I'm Gigi. I am one of the guest lecturers today. I'm going to be replacing Sydney as she's on vacation for a little bit, but yeah. So, all right, so today we're going to be learning about stereochemistry, and I'm going to go over all these terms, but chirality, and then different types of stereoisomers, enantiomers, diastereomers, and meso compounds. And Sam will go over a couple more other things about stereoisomers, and then go over some examples for us to practice with. Because I find stereochemistry a little bit difficult to grasp at first, but you'll get the hang of it with more practice. All right. And then because this can get a little confusing, we ask that you ask any longer questions at the end of the lecture, but feel free if something's like a burning question or really confusing you to pop in the chat or just to shout out loud so that we can clarify for you before like we go further with anything. And feel free to let me know if I'm talking too fast because I tend to talk fast as well. All right, but let's start off with this first question. Okay, so here are two molecules. Feel free to type it in the chat or shout it out. Are these molecules the same or different? It's the chime.
50-50 chance. Just take a guess.
All right, so some of you have DM'd me, so okay. So just so you know, this might have been a trick question, but actually they're just the same. And I'll go over why I'm asking these questions later. But so these molecules are the same. All right, and then we'll move on to this pair of molecules. Okay, so are these molecules the same or different? Feel free to shout out or type in the chat. And feel free to just DM me if you don't, if you're scared about your answer, just you could also just personal message me as well. Okay, so I see some of you answered. Okay, so again, I might have tricked you when I said this, but basically these are actually different molecules. And I'll go over why. So basically because if you see in the previous image, in this image, they look like the same, right? They look like mirror images of each other, but I'll go over why this particular molecule looks different. And so the reason is because they're called stereoisomers. So we're gonna learn something about stereoisomers. So basically, if you remember from Gen Chem, isomers are molecules with the same formula, but they're distinct structures. And so as a review, we have structural or constitutional isomers, which are molecules with the same formula, but different connectivity. So for example, like, glucose or fructose, or say, for example, here with the previous molecule that I showed you before, if you moved like this methane over here, then that would be like a constitutional isomer in that case. But so basically, back to stereoisomers. So these are molecules that differ only in their spatial arrangement of their atoms. So which is why in the previous question, when I said that they're different, it's because these are stereoisomers. And there are two different types of stereoisomers. So you have them as chiral molecules, which can be differentiated from the mirror image. And what I mean by mirror image is basically like literally a mirror image. So here, if you draw like a mirror, and you just draw like the reflection of that molecule, then that is a chiral molecule. Or well, that's a mirror image, because for the difference between a chiral and achiral molecule is how you can the relationship between the mirror images. So for example, like say, let's take my hands, right? So a chiral molecule would be like sort of like my hands, right? Where they can be differentiated from their mirror image. Because on the flip side, you'll have an achiral molecule, which can be superimposed. And superimposed means that the images can line up with each other, like exactly like atom for atom, they'll line up. And so let's take my hands, for example, right? So our hands are chiral molecules because they are mirror images of each other, right? But when you line them up, there's like no way to line them up because you see my thumbs right here, right? So they don't line up. They don't line up actually. So that's what makes them chiral versus like achiral, which makes them, if you can line up everything, then that would make a molecule like achiral. So for example, here I have this one example for like in terms of an achiral molecule. Draw a mirror here. And then you draw the reflection of this molecule. You can see here that these molecules can be superimposed because if I were to like just stick this molecule on top of each other, all the H's line up. So yeah. And feel free if this is confusing you to chime in with any questions, but also I'll go over like a little more in depth like about stereoisomers in general to make it more clear. All right, and then we'll go over some important definitions or important structures of stereoisomers that will help you understand more about the idea of stereochemistry. So we have stereocenters, in which an atom where changing the two attached groups to that atom change the configuration or change the spatial arrangement. So most often they're carbon molecules or sulfur or nitrogen. And these can be in the forms of alkenes or alkanes. So let's take this alkene on the left here. So here, if you take this hydrogen over here to this methane over here, right? And if you flip them to create this image, you have that makes this carbon a stereocenter because you flipped the position of these two. So once you flip the position of these two, so also another thing, a way to think about it is if you kind of break the bonds between these, between like the groups, that's how you can also determine if it's a stereocenter. Because basically you see how on the top there are hydrogen, there are these two hydrogens on the top, and then but with this image you have this hydrogen on the top and then this methane on the top as well. All right, and then here we have this alkane. So basically here this carbon is a stereocenter because you see here there's 4 different groups, right? So there's a CH3, a C2H5, and then C3H7, and then an H. And if you flip those two, like to this corresponding image, right? That makes it a stereocenter, right? Because you've changed the spatial arrangement. And also just a little side note, you see how here, like these molecules here, the CH3 or the C3H7. So those have a lot of like hydrogens or like carbon atoms attached to it, but they aren't stereocenters, right? Because if you switch any of these molecules here, if you switch any of these, that doesn't make it a stereocenter. All right, and so also, now we'll go into a specific type of stereocenter. So we have chiral centers, which is an atom, which is frequently a carbon atom that's surrounded by 4 different groups. And then also with chiral centers, they can also be called asymmetric carbons. And with asymmetric carbons, they have to be 4 different groups. So for example, right here, this compound right here, let me just erase a little bit to show you better. So this molecule right here is a chiral center, whereas with this alkane, this is not a chiral center actually, because it's not attached to 4 different groups. But this one is a chiral center. And for example, also here, this is also an example of like not a chiral center, but for an alkane, we could have this. So here we have, this is like a stereocenter, but not a chiral center, because if you flip the positioning of these two, then that makes it a different spatial arrangement, but they're not chiral centers because they're not 4 different groups. So, and then let me show you an example. So right now we're going to be using this thing called the model kit. Wait, let me pin my video. Okay, all right. So we have, so these are molecular model kits in which they're super useful for orgo, and we definitely recommend using them, especially when you first start with stereochemistry, because it can be kind of tricky if you just see these on paper. It's a lot easier to get it once you like look at it like 3D. So basically, all right, so here we have, I've made these molecules. So basically, for example, like each color represents like a different group, right? So we have a chiral center right now. So here we have this, and then we have its mirror image right here, right? So the reds here, the whites in, and then the greens up, and then the blues are facing towards me, right? Okay, so now what I'm gonna do is, can we superimpose these images? So remember that superimposing means that they have to like line up exactly. And if I do this, right, you can see here that, okay, so the blues line up, the greens line up, but the red and whites do not line up. And if I try doing it a different way, let's see, so these don't line up at all, but let's see. And then here we see the reds and the greens line up, blues and whites don't line up. So in any way that I try to match this, they do not match at all. They do not correspond. And so that's essentially what makes a molecule chiral, right? There's no way to line these up, even though they look like they could line up. So from the previous question before, when you thought they were the same, this is the reason why they cannot be the same, because there's no way that you can put these on top of each other and they will be the same exact molecule. Screen again. All right. And so there I demonstrated what like a chiral center is. But one thing to keep in mind, even though I've talked about like chiral centers and asymmetric carbons, is they're neither necessary nor sufficient for chirality in a molecule. And so so a molecule might have a chiral center, but the molecule itself may not be chiral. And so keep that in mind, because I'll go over something like that. I'll go over like something that makes this statement like make sense. All right. But now we'll move on to different relationships of stereoisomers. So here we have enantiomers. And so I sort of talked about this before with sort of like non-superimposed mirror images, right? So if we go over what a mirror image is, right? So if I basically drew a mirror right here, right? So basically you would have like, you have the mirror image. So you have the original molecule on the left, and then you have the mirror image on the right, right? And so they're mirror images of each other. But like I said before, they're non-superimposable on each other because there's no way that they can line up with each other. So that's the relationship of enantiomers. Another thing to keep in mind with enantiomers as well is if you draw an internal plane of symmetry. So let's just take this for example. Let me draw this right here. If you draw lines this way, you can see that also that this is not symmetrical, right? So that's why it's also called like an asymmetric carbon or like a chiral center as well, is that the symmetry does not line up here, right? So, and then again, with the same thing, if you're still confused about chirality, still think about your hands. You can't superimpose them on each other. Because like if you try sliding, like it won't work. Another way to think about it is if you flip them, right? Like they're mirror images of each other, but again, they don't line up. So those are enantiomers in a sense. And then we can move on to different types of other stereoisomers. So we have this thing called diastereomers, which are stereoisomers with at least 2 stereocenters, which are non-superimposable and non-mirror images. And so I'll show you what that means here. So I have more model kits right here. Okay. All right, so here we have this molecule, okay, right? So you see here, we have these blues in the back facing towards me, and the greens in the front facing towards you, and then we have the whites on the top, right? Okay, so what I can do to make this, to show you what a diastereomer is I take one of the stereocenters and I flip them. So I have one blue in the front and then a green in the back now, right? Okay, so we have something like this. And if I, wait, and I'll show you when I flip it back. That here, so here's the original molecule I had, and then here's a diastereomer that I had where I flipped the positioning of one of the green and one of the blue molecules. So if you flip or if you change the 3D or the spatial arrangement of one of the stereocenters, then you have something called a diastereomer. Because if you see here, they're not mirror images of each other because, like here you see you have like, you should have two greens like facing inward, but you actually have a blue right here. And then the same thing with the blues and the greens on the outside, right? So they're not mirror images, and by default, because they're not mirror images, they're not superimposable on each other. And so diastereomers can happen in the case of having at least two stereocenters, in which one of the stereocenters have their attached groups like changed, but the other stereocenter remains the same. All right, and then let me share my screen. Okay, and then we have meso compounds. So this can get a little tricky, but basically meso compounds are what I was referring to earlier about chiral centers being neither necessary nor sufficient in chirality of a molecule. So meso compounds are a chiral stereoisomer which contain at least two stereocenters and have a plane of symmetry. And so once again, I will stop sharing my screen and show you what I mean here. All right. Okay, there we go. All right, so this is an example of a meso compound, right? Okay, so basically we have two stereocenters and they are chiral centers. So, right, it's an asymmetric carbon. They have 4 different attached groups and they have two stereocenters right here and they have a plane of symmetry. So if I take my pen and make it a mirror, right, you have here like a plane of symmetry and they all line up. Like you have the blues in the front, the greens in the back, and the whites on top. So if you make a mirror image of each other, like that's what makes it a meso compound. So let's see, let me share my screen again. All right, and so that's what what I showed you before was a meso compound. And if there is a meso compound, it does not have an enantiomer, right? Does that make sense, right? Because the mirror image of a meso compound is itself and not an enantiomer, because an enantiomer has to be a non-superimposable mirror image. So you don't have like a pair basically of enantiomers in this case. You just have one meso compound. And so another thing to keep in mind with stereoisomers is, because I've gone over like different types of stereoisomers, it's important to know when you're given like a molecule, it's like how many stereoisomers are there in this molecule or can be created from this molecule, right? So here is a quick formula. So for determining the number of stereoisomers, we have here 2 to the power of the number of stereoisomers. So before we've been going over molecules with 2 stereocenters. So we have 2 to the power of 2. That means we can have 4 stereoisomers. Wait, spell this much wrong. And then if you have 2 to the 3, you could have 8 stereoisomers. One exception to keep in mind with using this formula though is that sometimes if you're drawing, so the best case to figure out like using this formula is the maximum number of stereoisomers that you can possibly have. But in that, you should still draw out all the molecules, because you need to figure out sometimes what they can do as possibly a trick question is ask you like how many stereoisomers can be formed by this molecule. And if you draw out all the stereoisomers, some of them can actually be identical. You'll see when if you can manipulate sort of and like rotate them around, that they're actually the same molecule. And so in that case, some of what looks like are 2 separate like molecules are actually identical. So that would like lower the number by 1. So instead you would have 3 stereoisomers instead of 4. All right, and so we'll go on to an example sort of that shows like the differences between all the different like stereoisomer relationships and the types of stereoisomers, and sort of using the vocab words like stereocenter and chiral center as well. So, all right, so we have a molecule right here. So we have this bromine right here, this fluorine right here, these methanes, and then these hydrogens. So if I were to draw the mirror image of this molecule, so here's a mirror image of this molecule. And then here, if I remember what I said before when I was talking about diastereomers, if you literally change sort of the spatial arrangement between one of the stereocenters. So here, let's take this, for example, this bromine and this hydrogen right here. So we'll flip those 2. All right, and then we can draw a mirror image of this. All right. Wait, oops, hold on. Messed up a second there. Sorry about that. Oh, I messed up on the top too. Sorry about that. Okay. Here, here. Okay, so ignore what I had before. Basically, right, we draw the mirror images right here. So here, so right, remember when I went over enantiomers, right? So these are enantiomers because these are mirror images of each other. And they're also non-superimposable. If you were to use your model kit, you would figure out that like there's no way you could put these on top of each other and have them be the same molecule, right? And so same with right here. These are also enantiomers because I just drew the mirror image of it. All right, and then so these are two pairs of enantiomers. Also, how to look at this is these are also two pairs of diastereomers. So remember what I said before about diastereomers not being so remember the diastereomers are still stereoisomers, meaning that they have the same chemical formula, but they're different in their spatial arrangement. So meaning that one of the stereocenters can be different, right? So if we take a look here, let me highlight this. Okay, so right here, if we take a look at these, so these two stereocenters are the same, but here, these two stereocenters are different because the attached groups have flipped. So in that case, this is what makes them diastereomers, is that they're different. The one of the stereocenters is different than the other one, but they still have one of the other stereocenters is still the same. Right, and then same goes for this one. If we also take a look at the stereocenters here, so let's see. So these ones are the same, but these ones are different. So that's what makes these two as well also diastereomers. So that's just a way to look at all the relationships and use all the terms that we talked about before, sort of in this like big example of it. Okay, so now we go on to here. So here's a little tree sort of like connecting all this stuff that I've talked about before and sort of also a summary of what I've talked about, of what I have been talking about like this past lecture for the past 20 minutes. All right, so for isomers, remember, they have the same chemical formula. And then we have constitutional isomers, which are different connectivity. All right, so now that I've been saying stereoisomers, diastereomers, and enantiomers a lot, does anyone want to remind me what stereoisomers are? What is different about stereoisomers? Feel free to pop in the chat or say it aloud. Okay, so stereoisomers have different spatial arrangements. Okay, and then for the different stereoisomers, we have enantiomers and diastereomers. So does anyone want to tell me, refresh me or the whole class on what enantiomers are?
They're mirror images that can't be superimposed.
Good job. Mirror images. All right, and then does anyone want to tell me what diastereomers are? Okay, non-mirror images. And non-superimposable. Okay, and then you can ignore the cis and trans isomers. We'll go over that in a different lecture. But yeah, so basically this is how you should think about like isomers and then stereoisomers. So these are all the different relationships and how they're all connected to each other. All right, and then on to Samantha.
Does anyone have any questions?
Oh, yeah.
First?
Does anyone have any questions about what I said? Also, Samantha will go over some examples to make it more clear. But if any of you have questions about what I said before.
All right. Do you want to turn off yourself?
Mhm.
You're mute. Okay. Good. It's not echoing.
Mhm.
Awesome. Hi, this is Sam again. Let me go ahead and share my screen. Is it gonna work? Is it gonna work? Yay! Can everybody see this? Or rather, can anyone not see this? Awesome.
You're good. Yeah.
Thank you. So I'm just going to very briefly go over optical activity. This is something that you'll also encounter in Orgo 1. And basically, one major difference between chiral and achiral molecules is going to be their optical activity. And so all optical activity is really referring to is this kind of like crazy procedure where you like take an isomer, you put it in solution, you put it through a polarimeter, and you're going to shine plane polarized light, also called PPL, through. And plane polarized light just means light that's polarized into one plane. So it's, light is normally going in literally all directions. In this case, it's only going in one direction. And so you shine this plane polarized light, this PPL, into the column. And so you're going to notice that chiral molecules will actually rotate this plane polarized light. And so an interesting phenomenon that scientists noticed is that for any two enantiomers, any pair of enantiomers, one enantiomer is going to rotate the beam clockwise. And one is going to rotate it in the opposite direction, so counterclockwise. And so this rotation is generally just noted in degrees. And so for any pair of enantiomers, this rotation is going to be, let's see, there we go, the same magnitude, but just in different directions. So like we noted, one is going to be going clockwise, one is going to be going counterclockwise. And so this is known as dextrorotatory for the enantiomer that rotates it clockwise, and levorotatory for the enantiomer that rotates it counterclockwise. And there are sometimes instances where you'll have a pair of enantiomers and you'll have an equal mix of the dextrorotatory and levorotatory enantiomer. And when you have this 1-to-1 ratio or an equal mixture of the two, you're going to call this a racemic mixture. This isn't a term we're going to go over extensively in OCSP, but you probably will hear it in Orgo 1. So I thought I'd just introduce you to it. And so something else you're going to want to notice is that achiral molecules, on the other hand, are not going to rotate plane polarized light. So we call them optically inactive. And last but not least, the observed rotation of your plane polarized light is going to depend on a lot of factors, not limited to just like temperature and wavelength, but also to like the specific chemical you're using. So we're going to briefly show you the equation for this. We're not actually going to use it for OCSP, but you will use it a bit in Orgo 1. So it's going to be specific rotation, which is this crazy alpha in the bracket, which is often a function of some kind of temperature and wavelength. So specific rotation, just in degrees. This is going to be equal to alpha observed, which is your observed rotation, also in degrees, over the concentration times, that's supposed to be an L. That is a terrible L. I'm just going to draw it like this. C, which is concentration. Because remember, you have some kind of isomer, some kind of molecule in solution, and you pull that into the polarimeter. So usually you're going to have some concentration of your molecule of interest, for example, maybe in milliliters of whatever solvent you're using. L is going to be the cell or the path length. And that's just going to be the length of the cuvette that you put your solution into. And so you might be wondering, okay, what's the difference between observed and specific rotation? So specific rotation is kind of like a physical property, like, for example, melting point or boiling point. For any given molecule, it's going to be different. Usually it's noted in literature for that molecule, whereas observed rotation is going to be the rotation that you actually see experimentally when you do this experiment. So like I said, for the purposes of this class, we're not really expecting you to know this equation. Generally, insofar as I remembered, the questions in Orgo 1 where you would use this were pretty easy, like plug and chug questions. You do want to make sure you're watching your units, and professors will go over this, so don't worry. What we want you to understand from this section is that chiral molecules are going to rotate plane polarized light. So like I said, they're optically active, whereas achiral molecules are not going to rotate it, so they're optically inactive. Cool. So now, like Gigi said, I'm going to be going over a bunch of practice from what we were talking about before. So first off, this is a question you're probably going to see a lot of different types of, but you're going to see two different molecules, and you want to think, are these molecules the same or different? So before I go over anything, I just want to remind you, you don't remember from Gen Chem, this D is deuterium. It's just an isotope of hydrogen. I think in deuterium's case, it's one neutron and one proton, whereas hydrogen is going to be one proton. But if you're just wondering what that D is, and you're like, what element is it? Just remember, isotope of hydrogen. And so you're going to look at these molecules, and you're probably initially going to see that this is where the main difference is, right? This is where they're looking the most different. This carbon over here has a wedge to deuterium and a dash to hydrogen. The one on the right just flipped. So this wedge to hydrogen and this dash to deuterium. So go ahead and either shout out or say in the chat, DM me, whatever. Do you think these are the same or different? I'm gonna wait a minute for responses. Don't be afraid of being wrong. This is a tricky subject. All right. I'm seeing responses. Thank you for everyone who's DMing me. And so this is a tricky question, but they're actually the same. So good job to those of you who've gotten it right. Basically, what you want to remember is there are often instances where you're going to see two molecules and superficially they look really different, right? You see this wedge in the dash, but they're flipped. But you actually, this is a case where you may want to get out a model kit if you have one. We're going to post some of Sydney's recommendations from last year after this lecture today. But if you want to go ahead and pin my video, Jennifer, give me the spotlight. Okay, I think this worked. I just made this molecule for you. Remember, it was just a pentagon. Deuterium is going to be the red guy. White is going to be hydrogen. So this is the first rendition of your molecule where the deuterium is sticking out towards you because it's on the wedge, hydrogen away. And so remember that the second version of this molecule was just this. So hydrogen out towards you, deuterium away. And so essentially, if you have a model kit, this is a good time to use one. You want to make your model, and then you can just manipulate it, flip it around, whatever. And you'll actually see that these two molecules, even though they look different on paper, they are actually the same. And once you get really good at this, once you do a bunch of practice, this will become like way more natural to you, and you'll be able to flip it around in your head and whatnot. Yeah, this is a good example of what Gigi was going over, where things that look superficially different are actually going to be the same. So these two guys are the same. Any questions on that? Awesome. And so let's add a second question onto this, which is, are these molecules, let me do this. Are these molecules chiral or achiral? And so remember, what's going to be the difference between these two? Remember, a chiral molecule, the mirror images should not be superimposable. Achiral, the mirrored images should be superimposable. So let's go ahead and draw mirrors for these two guys and draw their mirror images. If you remember from skeletal structures last week, whenever there's a hydrogen attached to a carbon, you really don't need to draw that. So I'm going to go ahead and omit him. So we've drawn mirror images for the left and the right, and we're going to notice that these two mirror images are superimposable. In fact, they look exactly the same, right? So we're going to say that this molecule is achiral. Cool. On to the next one. So is this molecule chiral or achiral? I'm going to give you a minute to think about it and go ahead, DM me, shout out, whatever you want in the chat, what you think it is. Awesome. Thank you for those of you who have responded. Remember, chirality, what is that going to mean? If the molecule is chiral, it's mirror images. Mirror image is not superimposable. So let's go ahead and draw a mirror image. Awesome. So we have our mirror image. And so note that these two molecules will be the same. So if we were to turn this guy around 180 degrees, you will get this as well. You can also see this on a model kit. If you would like me to do that out for you on a model kit, let me know. So you're going to notice that these two are not different. So they will be achiral. Any questions? Awesome. Almost there, guys. Just hang in there. Last few. So next one, does this molecule rotate plane polarized light? Remember from what we talked about before, if it rotates plane polarized light, is it optically active or inactive? What do you guys think? Optically, nobody's saying anything. Optically active. Remember, if it's optically active, it must be a pair of enantiomers. And that's going to correspond with the chiral molecule. So basically what this question is asking is this a chiral molecule? And so if we look at the stereocenter, we're going to notice that there are one, two, three, four different attached groups. So this is a stereocenter and a chiral center. Also, if we want to make sure it's chiral, go ahead and draw the mirror image, and we will see that the mirror image is not superimposable. Cool. So it's chiral, has both a stereocenter and a chiral center. And so one last thing to note here is that, make this smaller. Every chiral center, let me know if this is too small. Let me make it a little bit bigger. There we go. Every chiral center is a stereocenter. But not all stereocenters are chiral centers. And so hopefully this makes sense from what we talked about before. Remember that for something to have a stereocenter, you have to be able to move two of the groups and create some kind of different spatial orientation. Whereas for chiral center, all four of the groups need to be different. So it's kind of like the case of like the squares and rectangles. Every chiral center by default must also be a stereocenter, but not all stereocenters. For example, if they only have two different groups, not all stereocenters are going to be chiral centers. All right, next one. How many stereocenters in this molecule? So remember, for stereocenters, we're going to be looking at two different groups. Let's go ahead and look at these carbons in the middle. I'm going to make the leftmost one red, make the rightmost green. And so if we look at this red carbon, there's going to be 1, 2, 3, 4 different types of attachments. Go ahead and look at the green carbon, 1, 2, 3, 4 as well. And so are those two stereocenters? Yep, they're both stereocenters. Are they also chiral centers? 1, 2, 3, 4 different groups, also chiral centers. So this molecule has 2 stereocenters. Answer 2. And you want to make sure that you're looking at anything that could be a stereocenter in your molecule. So for example, these methyl groups here, you want to make sure they are not stereocenters. And so one way we can go ahead and look at this is by drawing him out. So remember R is going to be rest of the molecule. Remove this up a little. And so you're going to notice that if you were to manipulate any two of these groups, that's not going to change the overall spatial orientation. You're going to still get a molecule which is essentially the same as what you had before. So these methyl groups are not going to be stereocenters. They're not stereocenters. By default, they also cannot be chiral centers. All right, last question. So this one's going to be a little bit tricky, so just hang in here with me. But here is our question. So are these two molecules enantiomers, diastereomers, or the same? So let's go over these definitions first. So enantiomers are going to be non-superimposable, mirror images. Remember, diastereomers, also non-superimposable. But they are non-mirror images, so they are not mirror images. And so, same, you know what that means. We want to look at these two structures, and initially we're going to think, okay, well, what happens if we try to turn these guys around? Let's go ahead and try to turn them 90 degrees. How about this way? Turn that one that way, turn this one this way. What is that going to look like? Actually, first, before we do that, we can do that as well. Let's draw a mirror. You're going to see that these two structures are actually mirror images, right? Hydroxyl here, hydrogen on the wedge, hydrogen on the wedge. Sorry, hydrogen on the dash, wedge has the methyl group. And so these two are mirror images. So that immediately rules out diastereomer because remember, those have to be non-mirror images. Could be an enantiomer, could be the same. Let's look. And so once we draw them turned 90 degrees, we're going to get something that looks like this. Remember, methyl group will still be on the wedge. Hydrogen will still be on the dash. Hydroxyl up top. So you should get something that looks approximately like this. You're going to see that these are the exact same structure, right? So here's where shifting these around, drawing them different ways can help you figure out whatever the question's asking you. And so we're going to notice that these two, since they are the same, they're of course superimposable. You can put them on top of each other, get the same thing. They're not enantiomers, they have to be the same. Last but not least, we want to check, is this a meso compound? So remember, we define a meso compound as something with 2 or more stereocenters. Stereocenters, there we go. And also a plane of symmetry. So let me go ahead and zoom in on this guy. Are these going to have 2 stereocenters? Let's look. So carbon, carbon. If we were to count them, we'd see 1, 2, 3, 4 groups. Also 1, 2, 3, 4. So they are both stereocenters and chiral centers, but we just know that's sufficient. And also, last but not least, let's go ahead and draw a plane of symmetry. You're going to see that I can just cut these guys right in half. And these two parts are going to be symmetric. If I were to fold it over on itself, it would be the same. So it is also has a plane of symmetry. So it is, for this challenge question, these two molecules end up being the same image. They also end up being a meso compound. Any questions on that? All right, so that is the end of all our practice questions. Here's some general advice for stereochemistry, courtesy of Sydney. So she said to make flashcards via Quizlet or whatever you use to help you memorize definitions. This is especially helpful for when you're trying to differentiate diastereomers, enantiomers, all those different definitions that I know get like really confusing a lot of the times. Something else you can do is write the terms out. Focus on how the definitions are related. So like, what do diastereomers look like? What do the enantiomers look like? Something that might be helpful for you is to try to just build either models or just draw out a molecule and try to figure out what its diastereomer would look like, what its enantiomer would look like, that kind of thing. Related to that, also do. There we go. Now it's showing up. Wi-Fi hates me. Last but not least, do a lot of practice problems. We can give you some. You'll see some on your exams. You can also just Google them and find them online. And then if you can get a hold of a model kit, I know there's some in Baker. Sydney's recommendations will also put up. She tried to find ones that were the most affordable because sometimes the model kits can be kind of pricey. If you have friends who've already taken Orgo, a lot of the times they'll let you borrow or you can buy from other people for really cheap, that kind of thing. If you ever want to use mine, hit me up. But yeah, that is all we had for you. If anyone has questions, we'll stick around for a little bit longer, but if not, you guys are free to go early.
Thank you.
Yeah. Stop everybody.